Dear student, you could understand that that amount of torque depend on the value theta. When theta is 0, then P is sin 0, that is 0, torque is equal to 0. When theta is 180 degree, again torque is equal to 0. When torque is 0 and force is already 0, then this state we call the equilibrium state. Okay, this is in mechanical equilibrium. Force is equal to 0, that is translational equilibrium and no translational motion. And at the same time, is torque equal to 0, then it is called mechanical equilibrium. Now we will discuss the work done to rotate the dipole from one position to another position. That is, if you want to rotate the dipole from one position to another position, then we have to do some work. What is the amount of this work we will calculate? Okay. Work done. To calculate work done in rotational motion, what we do? Torque d theta. This just like force into dx, that is F dx is torque when translational motion is there. In case of rotational motion, how do we calculate torque? Calculate work done. Work done dw equal to tau d theta. Tau equal to torque. Okay. So you can see but dw is equal to tau d theta, then w equal to integration from theta 1 to theta 2, torque is equal to P e sin theta d theta. That theta 1 to theta 2 means we want to rotate the dipole from theta 1 position to theta 2 position. Then again P e is constant and sin theta d theta, and this integration comes to P e minus cos theta 1 to theta 2. Ultimately, putting the limits, w is equal to the work done equal to P e cos theta 1 minus cos theta 2. Okay, now what we are going to do? Now you will be able to find the energy stored in a dipole. Now, dear student, if we consider this dipole, you see, whatever the orientation, this dipole is system of two charges, charge 1, charge 2. The energy possessed by this dipole is equal to how much? 1 by 4 pi epsilon naught q1 q2 by r. R means the dipole length. Okay. So this energy, whatever position you are keeping, this energy remains constant. Okay. Now we have to find out what I am telling this. We have to find out a position or one orientation when a dipole will possess minimum energy. When this dipole is placed in an electric field and both are in the same potential, then you see energy possessed, additional energy possessed by this charge will be equal to this charge multiplied by V, and additional energy possessed by this charge will be equal to this charge multiplied by potential. Now both of them, if are in equipotential surface, then net charge, net work done or net energy will be equal to 0. Because Q into V and minus Q into V, that will be 0. Then what is this condition? You see, if we keep the dipole just perpendicular to the electric field lines, then you see this the plane perpendicular to electric field line will represent a equipotential surface. When both the charges are in equipotential surface, then net energy possessed by this dipole is equal to 0. Okay, but the energy what is due to the system of these two charges remains same. It is 1 by 4 pi epsilon naught q1 q2 as. This energy we cannot add or we cannot increase or decrease. We cannot use this energy also, because this system, the dipole, we are not going to modify. Okay, so the energy possessed by the structure of the dipole itself is considered to be constant, and let us consider this is 0. Then due to the presence of the field, when it is in equipotential surface, the total energy equal to 0. Now, what is the energy possessed by the dipole? If we want to say this, then what we need to do, we have to rotate the dipole from 0 energy position to any other energy position. Okay, Then what is the zero energy position? Zero energy position is when theta is equal to 90 degree. This represents what? Zero energy position. Clear? So potential energy of the dipole. Potential energy of the dipole. See, and work done is, it is also potential energy, means and work done on the dipole we have to calculate. This is equal to what we have got. This is theta 1 to theta 2 tau d theta, and this comes to what? Pe cos theta 1 minus cos theta 2. But when we are talking about for potential energy possessed by the dipole theta 1, that is we have to start our rotation from theta 1 equal to 90 and theta 2 equal to any position, arbitrary position theta. That is, we are going to find the potential energy when it is at an angle theta with the field. Then this work done will be equal to Pe cos 90 degree minus cos theta. This gives minus Pe cos theta, that is equal to minus P dot E, and this is what this work done is equal to energy possessed by the dipole. So torque, torque what we have got, torque equal to what? P cross E, whereas energy, potential energy possessed equal to P minus P dot E. This is potential energy. Now at different orientation, potential energy will be different. Okay.